We have two charges here, equally charged particles. It doesn't matter whether they're negative or positive, they're both going to do the same thing. They're going to fly away from one another because they have the same charge. They're held at 3.2 by 10 to the minus 3 meters apart. The initial acceleration of the first particle is 7 meters per second squared, and the second one is 9 meters per second squared, which means their masses have to be different. If we know the mass of the first particle, then we're asked to find the mass of the second particle and the magnitude of the charge on each particle. So they're equal charges, but they have different masses, which means that the exact same force gives a different acceleration. So for the first question, we are asked to find the mass of the second particle. So we can do this by just looking at Newton's second law. We can say the charge is equal for both particles. Okay. Therefore, F(1)2), the force of 2 on 1, is equal to negative force of 1 on 2. As in this figure, you can see here, you can see that these are in the opposite directions to one another, like this. That's nice. So, if M1 travels in the positive direction, we can say F(1)2) equals M1A1 and F(2)1 equals M2A2. So therefore, M1A1 is equal to negative M2A2. We just need to solve for M2 here. M2 is equal to M1A1 over A2, which is 7 over 9 times 6.3 by 10 to the minus 7. That's just the ratio of the accelerations multiplied by the mass. And that comes out to be 4.9 by 10 to the minus 7 kilograms. Okay, so the mass of the second particle should be less than the first particle because it acquired a greater acceleration. So that's that part of the question done. The second part is asking us to find the magnitude of the charge on each particle. Well, the charge is the same for each one, so we can just look at one of our forces. So we can say the magnitude of the force of 2 on 1 is equal to M1A1, that's just Newton's second law, but we also know that force is equal to K, Q1, Q2 over R squared. That's the definition of the magnitude of the electrostatic force. We can write this nicely as K Q squared over R squared. So therefore, Q squared is equal to R squared M1A1 on K. Therefore, Q equals plus or minus. We get this plus or minus because it doesn't matter whether the charge is minus or positive. We're still going to get this electrostatic repulsion. R squared M1A1 on K. So therefore Q is plus or minus R. We can take that out of our square root. M1A1 over K. Finally, we can now put in some values for this. Plus or minus 3.2 by 10 to the minus 3. Put in some values. 6.3 by 10 to the minus 7. Multiplied by 7 for the acceleration. Divided by K, 8.99 by 10 to the 9. And we get a nice answer for that of 7.1 by 10 to the minus 11 coulombs. We should probably write that as nanocoulombs, so 0.0 0.71 nanocoulombs. It's a nicer way of writing it. Right, we have a charged particle, an electron, with an initial velocity of 2 by 10 to the 6 meters per second in the x direction. So we've got the unit vector for that over here then. You can see. It enters a uniform electric field, and the electric field is 400 J newtons per coulomb in the y direction. So you can see the vector for that here. So it's coming in perpendicular to the field. We need to find the acceleration of the vector. We need to find how long it takes for the electron to travel 10 centimeters in the horizontal direction while in that field, and then how much is it deflected after traveling 10 centimeters in the x direction while in that field. So we can start by finding, using Newton's second law to find the acceleration. So I'll just write this down. We find acceleration using Newton's second law. Okay, and that we know that that's F equals ma. So remember, the Newton's second law is the thing that takes the forces and turns it into a kinematic problem via the acceleration. So in this case, the F is equal to QE. Now remember that a positive charge is going to follow those field lines. We're going to find that electrons should go the opposite direction. So we won't assume that. We'll just see that it actually pops out of this. So that's the electrostatic force. Electrostatic force exerted on Q by E. So as soon as you put a charged particle into that electrostatic field, the electric field, it's going to feel a force. And we know that the field lines are defined, the direction is defined by the direction a positive charge would go. So there, because of this, we can equate those two things, and we can say QE is equal to mass times acceleration. That's nice. So therefore, the acceleration is equal to Q on M times E. So acceleration is equal to Q on M, and E was 400 J. And that is, well, the charge on an electron is 1.602 by 10 to the minus 19. Not given to you in the problem, but a pretty common constant is the electron mass, which is 9.11 by 10 to the minus 31 kilograms. Very, very small number. And we have to multiply that by 400 J. And we get an answer then for the acceleration, which is negative 7 by 10 to the 13 J meters per second squared. Okay, so that makes sense, because if we put an electron in here, it's going to go, an electron's going to want to go like this, the opposite direction. So that's where an electron goes, the opposite direction to the field lines. And a positive charge injected in here would go like that. Remember that for the exam, kids. So the next part of the question is asking for how long it will take for the electron to travel 10 centimeters in the x direction while in that field. So what's the acceleration in the x direction? No acceleration in the x direction. Okay, the field is only acting perpendicular to the motion, so it's only acting in the y direction. So there's no force in that direction. So therefore, the time taken is just going to be from velocity equals distance over time, so distance over velocity, which is 0.1, so 10 centimeters, divided by the velocity, which was quite large, 2 by 10 to the 6, which is equal to 50 nanoseconds. So it takes this electron 50 nanoseconds, coming in quite hot. It's going to take 50 nanoseconds to traverse 10 centimeters. The last part of the question is saying how much and in which direction is the electron deflected after traveling that distance. So we know it's just going to travel some distance this way, and we know how long it takes to do that. Well, it's also going to take the same time to be deflected this direction as well. So that time here is the same as that time there. So we need to find what that deflection is, so that we're looking for delta y. So looking for the displacement in the y direction. We know it's 10 centimeters in the x. We want to find out for the y. So we have some data. We have the initial velocity in the y direction is 0. The time taken is 50 nanoseconds. 50 by 10 to the minus 9 seconds. We also have the acceleration in the y direction is minus 7 by 10 to the 13j. So that's a vector, remember. So that's some information we have. Well, we're looking for delta y, then we can go to use this kinematic equation. Delta y equals v naught y t plus ayt squared on 2. Nicely, this disappears, and we can plug the values in now. Negative 7 by 10 to the 13 j times t squared, which is 50 by 10 to the minus 9 squared, and we need to divide all of that by 2. And when we do that, we get an answer which is negative 8.75 by 10 to the minus 2j meters. This question has a couple of parts. In figure A, we have particles 1 and 2, each with 20 microcoulombs of charge. They're separated by 1.5 meters, so D is equal to 1.5 meters. And we're asked to find the electrostatic force on particle 1 due to particle 2. And in the second question, we're asked to find the magnitude of the net electrostatic force on particle 1 due to particles 2 and 3. So we can be a bit clever with that second part of the question, but we'll solve question A first. It's a bit easier. So A, we want to find the force of this particle on this particle. So we can just use our electrostatic force equation. We want to find the magnitude of 2 on 1. That's equal to K. Remember that K is just 1 on 4 pi epsilon naught. And it's 8.99 by 10 to the 9 is the magnitude of it. So it's easier to write our equations down. So it's KQ1, Q2 over R squared, where R is the distance, so we'll call it R12. It's the distance between them. So those two charges are equal, so we can just say KQ1 over R12 squared. And we can just put some values in for that now. We have 8.99 by 10 to the 9 for K. Our Q is 20 by 10 to the minus 6. And don't forget to the squared term here. Squared. All divided by 1.5 squared, because that's the distance between them. And I get an answer for that quite simply of 1.6 newtons. Now the second part of this question, it's going to help us to make a nice coordinate system to look at the symmetry of the problem. This is an equilateral triangle, okay? So if I draw my x coordinate this way, and then I draw a y coordinate this way, you can see that I can exploit the symmetries of that nicely. So if we're looking at the force on 1 from 2 and 3, you can see that the x component of that force is going to cancel out. The force from 1 is going to cancel out the force from 3. So there's going to be no force, net force, in the x direction from those two charges. So that's why I chose that nice coordinate system. So we really only need to look at forces in the y direction. So I'll just write a couple of things down there. We'll say B, draw an appropriate coordinate system to look at your symmetries. And forces in the x direction cancel out. So we only need the forces in y direction. Right. So this is nice. We can draw a purple triangle up here to look at these forces. You can see that the force of 2 on 1 is going to be pushing in this direction. We'll call that force 1, 2. It's going to have a y component here, and we'll call that F12y. Now, because it's an equilateral triangle, we have 60 degrees here, which means we must have 30 degrees here. So we've done this a million times now. We've been able to find the length of F12y if we know what the length of F12 is. So we can then say, right over here, consider that purple triangle. We can say that F12y is equal to F12 cos of 30 degrees. Okay, we're just trying to find the length of that guy. Okay, and that is, we figured that out in the last question. We know what the magnitude of that force of 1 on 2 is. We know it's 1.6 newtons. So we go 1.6 times cos of 30, and we get 1.39 newtons. So that's the force of 1 on 2. Well, we know that the force of 3 on 2 is just going to be that as well. So, you know, the force of 1, 2 in the y direction is the force of 1, 3y. So we just have to double the force then to see what the total force on call it Ft is F12y plus F13y, which is 2 times 1.39, and that comes to 2.77 newtons. Okay, so we exploited some symmetry here. We exploited a good appropriate coordinate system, and then we saw that we could get rid of the x components of the forces and only consider the y. And then we know that the force from 2 and 3, the y force, is exactly the same because the charges are all the same. Too easy. We have 4 charges here. They're all emitting an electric field, producing an electric field, and the electric field right in the center here is going to be the sum, the vector sum of all of those fields, and we want to know what that value is. So the total electric field is going to be the electric field from 1 plus the electric field from 2 plus the electric field from 3 plus the electric field from 4. So that would be the brute force way of doing that. We could just use our electric field is equal to KQ over R squared with our little unit vector like that, and just find out what it is for all of them and add it up. But we could use some smarts here, and we could use some cancelling of the field to make this a bit easier for ourselves. So first of all, let's make it a bit easier for ourselves by saying let Q1 equal capital Q, which is 10 nanocoulombs. Then Q2, sorry, is going to be negative 2Q. Q3 is going to be 2Q, and Q4 negative Q. Okay, if you just look at those charges that are given in the problem. So we can redraw this. So we can redraw our distribution of charges, so we can redraw this, considering that the field is partially cancelled. The field is partially cancelled across the diagonals. I'll explain that in a second. Okay, so I'll write the charges in here. This Q1 is Q, this is negative Q, and this is 2Q, and this is minus Q here. You can see if we look across that Q2 partially cancels out Q1 Q2 partially cancels out the charge from Q4, okay, and also Q3 partially cancels out the charge from Q1 across the diagonals. So we can rewrite there. We can write, and I'll just write this. We can have an equivalent charge distribution. Equivalent arrangement, we'll call it, of charges. That gives the same field. Okay, so I'll get around to drawing that over here. So we can now say that we can get rid of this guy, and we can get rid of this guy, because we can basically they get partially cancelled out by this one and this one across the diagonals. So we end up with, I'll draw the point P in the center again here, point P we're trying to find. We now can effectively say we've just got this charge here and this charge here. That's 1 and that's 2. And the effective charge then of this guy is going to be minus Q, because some of it was removed by this guy. And then this one down here is going to be Q, effective charge, because some of it was removed by this guy. So this is just an alternative arrangement. We basically cancelled out this one and this one based on just the cancelling out of charge across the diagonal. So then we can figure out that the electric field due to 2 is going to push this way because it's a positive. It's going to push a positive test charge that way. We'll call that E2. And then this guy, Q1, is going to give us an electric field pointing that way because a positive test charge at point P is going to get pulled towards charge 1. So we end up with these two electric fields pointing this way. So this means that if they're equal, well, we should be cancelling out in the x direction, but we'll see if that happens. Right, so we've just done a little bit of rearrangement, just being a bit tricky here. So, therefore, the electric field due to 1 is K Q over R1 squared times the unit vector. Okay, so how are we going to work this out? Well, I'll draw the charge up here. So talking about Q1, sorry. And here is the center. Okay, so we can draw a unit vector. It's going to be a unit vector pointing this way. This is our R1. It's going to be pointing that way. So that's going to be equal to, it's going to have equal components. It's going to be length 1. So it must be 1 on root 2 I plus j. So that's our unit vector pointing in that direction. Now, the distance between here and here, so this is Q1, remember? This is our charge of minus Q here, so that's 1. That distance is, so we'll call it R12. If this distance here, you can see that's this distance here. If this must be A on 2 here. So this must be A root 2 on 2. Okay, it's just A on 2 squared plus A on 2 squared all square root. So we figured out all the stuff that we need to put into this equation now. So that's equal to K, Q, R1, sorry, this should just be R1 up here, sorry, not R12. Let's not confuse things. It should just, up here should just be R1. Okay. So R1 squared is just going to be A squared root 2 squared over 2 squared, which is going to be A squared on 2. Okay, all I did was take this value here and square it. And then I have to multiply by my little unit vector, this guy here, and I get 1 on root 2 I plus j. Okay, so now I have my unit vector, or I have my electric field vector for E. That's nice. I can do exactly the same thing for the second field, but it's going to be a different direction now. It's going to be this direction. So our unit vector is going to change. So we have K, Q over R2 squared. Should be a 1 here. And our second unit vector. So our second unit vector, well, let's just write this bit. Again, that distance is going to be A squared on 2 once we square it. The unit vector now, you can see for this one, it's going to be the same, 1 on root 2, but we're going to have a minus I direction here. Okay, so we're going to get minus I. And we still get a positive J for the direction of the electric field. Right, so now we have those two vectors, we can write the total vector. This is E1 plus E2. So instead of having 4 to do this for, we only have 2, and we use a bit of symmetry. It's going to be K, Q over A squared on 2, 1 on root 2 is going to come out the front. And then we just have to add these two together. So we get I plus j minus I plus j. Okay, so that comes out to be, we get K, Q over A squared on 2, 1 on root 2, 2j. That's nice, and we can tidy that up a little bit and say that that's 4kq, which is a very terrible radio station, over A squared root 2j. Beautiful. So that makes sense because if you look at this distribution of charges here, then we should have an electric field that's pointing only in the j direction because the E2 and E1 cancel out in the x direction, as you can see from that diagram. So now we can put in some values. 4 times 8.99 by 10 to the 9 times q, which is 10 by 10 to the minus 9. And we've got a squared on the bottom. We know what this is. Just underline this. We get 5 by 10 to the minus 2. Don't forget to square it, times root 2. And that comes out to be 1.02 by 10 to the 5j. So it's pointing in the j direction, the electric field, which we would hope to be happening. And the units are newtons per coulomb, or we can use volts per meter. So we looked at symmetry here. We could have just found E1, E2, E3, E4 and just added them all together. But we just used a bit of a symmetry argument. You should try it for the other way around. So try it this way, just as an exercise, and you should get the same answer. But it's good to look for these symmetries in the problems. Right, so we have two charges here sitting on the x-axis, so we're only one-dimensional, makes it nice and easy for us. There's a charge of Q1 is minus 5Q, and particle 2 is positive 2Q. So it's kind of like a dipole, but a little bit different. One's got a larger charge. We'll be able to see the field from that in a second. I'm going to pop up a nice diagram of that you can see. They're fixed on the x-axis. So as a multiple of distance L, at what coordinate on the axis is the net electric field of the particle 0? So you can have a think about, whereabouts that should be. So So yeah, we'll find that out in a second. We'll work it out. So what we need to do here is then say that the net field from Q1 plus Q2 is 0. So therefore we can write it this way: the total field, which is the total field from 1 plus the total field from 2, equals 0. So let's have a think about just one point, one charge. We'll call it this one at x equals 0, and you've got this other one at x equals L. Let's think about the Q1 charge. So at some point, we don't really know what that is yet, at some point x, the field due to Q1 is, well, the magnitude of it, for starters, E1, is going to be K Q1 over x minus 0 squared. That's just basically saying the distance between the origin, where the charge is, and the x position that we're looking at what the field is. You know, is it here? If it's here, that's x is there, then we can say that, you know, the distance between here and here is x minus 0. Okay? So that is going to be K Q1 over x squared. So we've got one equation there. So we can do the same thing. So similarly, for Q2, we can find the field at any point near Q2, magnitude of it. It's going to be K Q2 over x minus L squared. This is basically the same thing. We say this is our x point again over here. We can find out the distance between here and here just by going x minus L. So that's the R on the bottom. Okay. So therefore, we can say, if they're equal to 0, then we can say that the magnitude of the electric field from 1 is equal to negative electric field from 2. Okay, because they're both equal, add them together, they're equal to 0. We can say that as well. So therefore, K Q1 over x squared equals K Q2, or negative K Q2Q, over x minus L squared. So we're going to get rid of our k's there. We're trying to find a value for x here. That's what we're trying to solve. So we get Q1 over x squared equals negative Q2 over x minus L squared. So we want to try and get these x's by themselves. We'll get them on one side, so we can go x minus L squared divided by x squared. So we're just crossing across, is equal to negative Q2 on Q1. So all we're doing here is algebra to try and get x by itself. We find the square root of both sides. We get x minus L over x equals root negative Q2 on Q1. Don't worry about that negative sign because we know that Q2 is a negative sign anyway, so we're okay. So therefore, if we just divide through on this side by the x, we get 1 minus L on x equals square root of negative Q2 on Q1. So then L on x equals 1 minus square root of negative Q2 on Q1. Therefore, x, just by doing some other rearrangement, is equal to L over 1 minus square root of negative Q2 on Q1. We're getting there. We can just plug some values into that. We get L over 1 minus square root of 2 on 5. And we get an answer for that of 2.72 L. Okay, that's our answer. So at some distance, 2.72 L, the field from Q1 and Q2 will cancel out. So here's a simulation of the field lines from those two charges. So this would be Q1 and this is Q2. separated by a distance, let's call this L. Our answer said at around about, 2.7 L, so around about here, we should be seeing a minimum in the field. And that's what it looks like here. You can see that there's the field lines are sort of going away from this region. So that's the point we're talking about, where the total field is equal to 0. So very hard to visualize a field like this because of the difference in these two charges, the difference in the magnitude of the charges, but that's what it looks like.